Welcome back friends to our next video lecture. Today we will be covering about a random variable and a mathematical expectation. So this entire lecture is divided into two parts. So today we will be covering the first part of the lecture. So let me remind you that I am your Professor Dibbojyoti Bhattacharjee from the Department of Statistics, Assam University. And we will be studying this particular lecture in two parts. In the first part that we'll study today is actually about different terminologies and theorems that are connected to either random variable or mathematical expectation. And in the next part of the lecture, we'll be solving some problems related to the chapter. So here we go. Now, we know that whatever we whenever we perform an experiment, these experiments that we perform can be classified into two parts. There are two types of experiment as a broad classification. First part is the deterministic experiment, and the other type of experiment are called as random experiment. Now, what is the main characteristic of the deterministic experiment? The main characteristic of the deterministic experiment is that the outcome of the study or the value for which we are in search of remains same every time the experiment is performed. That the value is not changing, it rather remains the same every time we perform the experiment. So this is an aspect of deterministic experiment. However, in case of random experiment, the result is a variable. That means the result changes every time we perform the experiment. Actually, there is a set of possible outcomes of a random experiment, and we know that particular set of possible outcomes. We know that the outcome that we get will be one of the values uh, taken from a particular set, but which value will appear when the experiment is actually performed, that is not known to us. That is a matter of chance, and hence such experiments are called as a random experiment. Here we go in the next slide and try to look at some such examples of both like deterministic experiment as well as random experiment. So here are some examples. First is that this boy, he is measuring the length of a table. Now measuring this length of a table, whether this boy measures once, twice, thrice or n number of times, or even if I go and measure, you also come and measure, we will end up in getting the same length. That means the result will remain the same provided our method of measurement is perfect and we are using the same scale. The outcome of the experiment will remain the same. So that's why it is a example of a deterministic experiment. Another example is the distance between two places. Say the distance between two places, it never changes, given that the road is same. If you travel by the same road, its distance always remains the same, so it never changes. So this is another example of distance deterministic experiment. Now weighting a 1 kg packet of rice. Now suppose I have purchased 1 kg packet of rice from the shop, and before purchasing I weight it. Sometimes it might be little more than 1 kg, sometimes it might be little less than 1 kg, but the net weight, whatever be the value, will remain the same as many times I perform the experiment after that. So unless and until we take away some rice or add some rice to it, other than that, this will remain the same. So these three examples are actually all examples of deterministic experiment. As you see that when we perform the measurement or when we perform this particular experiment, the result of the experiment never changes, rather it remains the same. So that's why this is an example of a deterministic experiment. Let us look at this. These are examples. Let us take some examples from random experiment. Throwing of a die. Now suppose I throw a die. Here you can see two die, but then they are actually one die thrown twice. In the first die, you can see that probably 6 is going to appear, and in the second die, 2 is appearing because that is at the top. So we may assume that here what happens in case of random experiment, every time we throw the die, we don't get the same result every time. The result keeps on changing. Yes, some cases we may get the similar result, but it will change soon after in the next trial or in the next to next trial, etc. Now here what happens, you know the set of all possible outcomes. That is, you know that when a die is thrown, you will get either 1 or 2 or 3 or 4 or 5 or 6. So you know the set of all possible outcomes, but you don't know which outcome will happen when the experiment is actually perform. So that's why this example is an example of a random experiment. Let us take another example. Waiting for a bus. Suppose you go out and wait for the bus every day. Now every day the bus you may not have the same waiting time. Someday you may approach little bit early to the bus stop, wait for a longer time. Sometimes the bus may be late, making you wait for a longer time. Sometimes when you come, the bus has already left, so you keep on waiting for the next bus. So what actually happens is that this particular waiting time for the bus is not same, but rather it varies. So this is another example of a random experiment. And then say stock price. Suppose a closing price of a stock. Every day the closing price of the stock is not same. Sometimes it goes up, sometimes it can go down also. So this is another example of a random experiment. I have another example of a random experiment. Suppose time to survival of an individual. Now, this is a patient you can see probably in the ICU having some serious illness, and we are waiting for the recovery of this particular gentleman. So this recovery time or time to recovery of the gentleman is not fixed, rather it may vary. Sometimes a patient may take more time, sometimes a patient may take less time, sometimes a patient may not survive, and in that case the time to recovery becomes infinity. So this time to recovery is a variable which is a random variable, and hence this is an example of a random experiment. So here we set some examples of a random experiment and also deterministic experiment. Now our focus is on random experiments, so let us analyze in details in random experiment in subsequent slide. But here I like to tell you one interesting thing. For example, in throwing of a die, the possible values are 1, 2, 3, 4, 5, and 6. So these are called as a these are all discrete values, integral values which are discrete. So this is an example of discrete random variable. Now waiting time for the bus is continuous. Stock price, it is a continuous variable. It can take any value within a particular range. Now, if you look at the survival, time to recovery. Now, this is a time. A time is a continuous variable. But if we look at say whether the person recovers or does not recover, that is the stage. That means if he recovers, we consider 1. And if he does not recover, then we consider it as 0. Then this time, that is second example, of whether the person recovers or not is also a random experiment. And in that case, the concerned random variable takes the values either 0 or take the value 1. So that means it might be discrete, and depending on the type in which you define the variable, it may also be continuous at times. Now, let us look into some more details about the random variable, because to understand the entire process, we need to do this. The outcome of a random experiments is represented by a variable x. So whenever we perform a random experiment, whatever outcome we get, that outcome is represented by a variable x. We are always aware about all the outcomes of the random experiment. That means whenever a random experiment is performed, we cannot be sure about the outcome of the random experiment, but we are aware about the possible values that the random experiment can give us, or the possible values that can be generated from the random experiment. The set of all these possible values is represented by capital S, or sometimes it is also written as capital omega. Capital omega symbol is like this. So this capital omega or sample space S, this is called as represents the sample space, and it has the set of all possible outcomes of a particular random experiment. Sometimes these might take discrete variables like 1, 2, 3, 4, 5, 6 in throwing of a die, or this might be a continuous variable also, like say waiting time for a bus. It may start from 0 and go up to infinity. That means theoretically it may be that the bus never comes. Anyways, this particular set which is called as a sample space might be having finite number of values. It may have infinite number of values also. A random variable is a function that maps the points of a sample space to the set of real numbers. So some people tell that random experiment is not actually random variable is not actually a variable only. It is rather a function which maps the outcome of the random experiment to a set of real numbers or to a subset of real numbers. So this is how some people define a random variable. let us try to understand this with the help of this animation. Suppose I am tossing a coin 3 times. Okay, or I am tossing 3 coins one by one. It is the same thing. Means tossing a coin 3 times one after another, or tossing 3 coins at the same time. They are actually assumed to be the same thing. And whenever we toss this, we have these possible outcomes. That means let us have a look at all the possible outcomes. That whenever you toss a coin 3 times, this is the possible. So this is our sample space. This is the all possible outcomes that we can get out of here. That means all three are heads. Two of them are head. First two of them are head. The second one is a tail. First one is a head. We have a tail in between, and then another head. First one is head. The second two are tail. In this way, we can get different outcomes of the random experiment. Now, this we represent a random variable. So, this random variable we represent by x. It counts the number of heads in 3 tosses of a coin. So, here you see we have 3 heads. So, the number of x is 3 in this case. For this case, we have the value of x is 2. For this case, 2 heads. So, value of x is 2. Here, only 1 head. So, value of x is 1. Here, 2 heads. So, value of x is 2 once again. Here, only 1 head. So, it is 1. Here we have 1 head, so it is 1, and here there is no head, so it is 0. So you see this random variable x, it takes the value 1, sorry, 0, 1, 2, and 3. And 1 and 2 are appearing more number of times. That is, 2 is appearing 3 times, 1 is appearing 3 times, and 3 and 1 are appearing only once. That means if we look at what are the possible values of the random variable x, that means these are the possible values of the random variable x. That means it can take the value 1, 0, 3, 2. So we started with tossing of a coin. Based on the random variable, we actually reached to some numbers. Now, this is a subset of a real number, you can tell. So, this mapping is done by the random variable. That means random variable maps a random experiment to a set of numbers, which is a subset of a real number set. So, subset of R, that is real number. So, this is why this variable, random variable, is sometimes some of the authors have claimed that random variable works like a function. That means it takes values 1, 0, 3, and 2, 0, 1, 2, and 3. But all of them are not equally probable. Some of them, as we have seen, that 1 and 2 are more probable, and 0 and 3 are less probable. That means if we repeat this experiment a large number of times, we will find that 0 and 3 is occurring less compared to what is happening with 1 and 2. So this is how this random variable can be explained. Now I take another example. Now here we are looking at a crowd of people. You see people from different uh, 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 groups, ethical groups are standing before us in the form of a queue. And we are interested in measuring the heights of each of the individuals. Now, what happens here when we measure the height of the individual, let x be a random variable which represents the height of the individuals. And you may find that the person with the shortest height, probably this, sorry, probably this particular small child, this one, her height say is around 120 centimeters, and the tallest person of the group, I think this is the tallest person. Okay, his height is around 190 centimeters. That means in the entire group, the values of the heights of the individuals are lying between 120 centimeters to 190 centimeters. So these are the possible values that x can take. Now, here you see in the previous example and this example, what is the difference? In the previous example, we had the random variable x taking some discrete values, 0, 1, 2, 3, like that. Here it can take continuous values because the heights, as you can see, lies between 120 centimeters to 190 centimeters, but they can be fractional also, like 121.5 centimeters, someone may have height, someone may have height 184.6 centimeters. So fractional values are also possible. That means it takes any value within a particular range from 120 centimeters to 190 centimeters. So such random variables which can take any value within a particular range are called as continuous random variable, continuous. And the previous example where the random experiment, random variable takes some fixed discrete integral values, these are called as a discrete random variable. discrete random variable. So we have discrete random variable and continuous random variable. So in these examples, through these examples, we have learned about random variable. We have learned about a discrete random variable, and we have learned about continuous random variable. We have learned about the random experiment, which is the basis of a random variable, and we have seen how random variable changes depending on the type of experiment that you are performing. Now, here we reach up a stage where we can define different types of random variables. So let us look at different types of random variables. First, we look at a discrete random variable. Here a random variable x assumes only a finite number or countably infinite number of values. That means this random variable x takes some finite values which are generally integral, or countably infinite number of values. That means countably it is infinite, but it can take some say discrete values like 0, 1, 2, 3. It may go up to infinity, but it does not take value in between. It takes some fixed values. In all such cases, a particular random variable is called as a discrete random variable. The discrete random variable are represented by Latin letters, uppercase, that means capital letters, x, y, z, or x1, x2, y1, y2, z1, z2, z3, etc. And the corresponding value taken by the random variable is written by small Latin letters, that is small x, small y, small z, small x1. That is capital X equal to small x, capital Y equal to small y, like this. If I write that capital X equal to small x, it means that capital X is a random variable which takes a value small x. The particular value of the random variable is represented by small x, and particular value of the random variable y is taken as small y. Now, these are some examples of discrete random variable. Now, suppose a sales representative is approaching a customer to sell a product. So, a customer entered into a shop with an intention definitely to buy, provided he or she gets uh, the article which he or she wants to provide as per his or her requirement. So the person goes inside the shop, and the person is attended by a sales representative. The sales representative is actually displaying or keeping before the customer the product that he or she is asking to buy. And then the customer is asking different questions and putting different queries related to the sales and service of the product, price, quality, and then what is the after sales service, etc. Now, at the end of the conversation, the customer either gets satisfied with the price, quality, etc., and purchases the product, or do not purchase the product, goes to some other store for purchasing the product. That means the attempt of the sales representative is either ending up with the sale of the product, or the product is not being sold. That means if we represent X as a random variable, that is what is ultimately happening with the sales representative. Now we can put it in a random variable, because we know that this situation we have to connect it to some real numbers or some numbers. So we can tell that, okay, X equal to 1 if the product is purchased, if purchase is done, if purchased, and equal to 0 if the product is not purchased. Or you may write otherwise, equal to 0, otherwise means not purchased. Now here you see your random variable X only takes two values, 1 and 0, but well, that is how this random variable is defined. Now face value that appears when a die is thrown. Now let us look at this. So suppose you are throwing a die. Now you know that a die has 6 faces. So when you actually throw that particular die, you will get either 0, sorry, not 0, either you will get 1, 2, 1, 2, 3, 4, 5, 6. So this is your sample space. This is your sample space, and a particular value, say any one of these values, will be taken by this. So if X is a random variable which will represent the outcome of a die throw, then X equal to small x, and this is equal to the face value that the die is thrown. Now, number of people standing in the queue. Now, the number of people who are standing in the queue, so that may be may be 0. The queue may not have any person. So it may be 0. One person might be there in the queue, 2, and then it can go up to infinity. So this is an example of a countably infinite number. Countably infinite number. So the number is discrete 1, 2, 3, 4 like that, but it can countably go to infinity also. Infinite number of people in the queue. Definitely there will be some number where the queue will stop, but that might be very large. A number of calls to potential customers before the first one who agrees to take a given insurance plan. Suppose an insurance sales representative is there who is actually trying to contact some of his previous customers and explaining about a new insurance policy which has come over. So he is trying one after another, since he is known to the people, so they are actually conversing with him, picking up his phone and talking with him, and then he is trying to pursue the sale of a particular insurance policy and the convince the individual, gain their confidence. Now he always have their, has their confidence because he has already sold some policies to these individuals. This is his known base of customers. Now suppose he calls the first person, denies to purchase because he tells that he doesn't have money. The second person tells that he has already invested a lot in those policies. The third one tells that he is more interested in share market than purchasing an insurance plan. But the fourth one tells that he is in a position and, well, wants to purchase the insurance policy. So the value of the random variable x, which represents the number of calls before the first one agrees, is equal to 3 in this example. So if the first one agrees, the value of x is 0 because the first person agrees. So no call before that, no unsuccessful call before that. So x equal to 0. A second person agrees, then the number of unsuccessful calls is 1. So x can take the value 0, 1, 2, and dot dot dot, it can go up. So this is about the number of phone calls before the first person agrees. So we have seen through these examples that x, that is the random variable, can take different types of variable values. It can be a binary variable like taking the value 0 and 1. It can be a particular finite set of numbers, discrete numbers 1, 2, 3, 4, 5, 6. It can be infinite set of numbers, which is called as countably infinite. That is discrete, but it can go up to any number. So these different, and all of this comes under discrete random variable example. So let us go to the next type of a random variable, which is continuous random variable. Here the random variable x can actually assume any value within a given interval. That is, the random variable can take the real number x lying between two other real numbers, that is a and b. There is time taken to complete a service. So say time taken maybe 10 minutes, maybe 12 minutes, maybe 15, 20, 70 minutes. So time taken to complete a service. So say some person have come to give you a service to your home. So maybe cleaning up your AC. So your AC is been serviced. Now the time taken. Now this is a continuous random variable because it can take fractional values also. But obviously servicing of your AC will cannot be done in zero time. Some time will be required. Also, it cannot end up at an infinite time, but it can take some values within a particular range of value. Weight of individuals in a crowd. Now, weight is something fractional, though generally we tell weight as if it is an integer, like his weight is 72 kgs, my weight is 90 kgs, etc. But actually, these are fractional. Means when you take the weight, it will not be exactly that much, but then it can take any value within a particular range. Human weight may vary, say, from 45 kgs to 120 kgs of a group of individuals. It will find that vary. So it can take any value within a particular range. Waiting time for a vehicle. Already we had cited this example earlier. A person was waiting for a bus, if you can recall. So closing price of a stock on a given day. So closing price of a stock. So it may take any value within a particular range. So these are all examples of continuous random variable. And then here we cannot write the entire set because there are many possible values, but we generally write the highest value and the lowest value that the particular random variable can take, and that's the way in which I define the random variable, that is the continuous random variable. Next, we go a step forward and discuss about the probability distributions. A distribution of values taken by a random variable x and their corresponding probabilities forms a probability distribution. Now, earlier we had seen that the random variable x can take different values. Also, in the example of tossing the coin 3 times and counting the number of heads, we have seen that the different values taken by the x are not equal in number. Some values like 0 and 3 are very less. However, 1 and 2 are appearing 3 times each. So what we understand from that example is that all the values taken by the random variable are not equally probable. Some of them might have more chances than the others. The probability distribution of a discrete random variable is called as the probability mass function. Now, if we arrange the different values of x, and along with that, if we state the different values of the probability of x, probability that x takes for different values of x, then that particular tabular form is called as the probability distribution. And the probability function is called as the probability mass function, because we do not get probabilities at all different points. We get at certain fixed points. So probability is considered as the mass which actually accumulates around a point, like x equal to say 0. We have one probability, x equal to 1. We have one probability, x equal to 2. We have some probability, and x equal to 3. I have some probability. So some of them may be same, some of them may be different. So that's why we need to actually include this probability mass function. Probability distribution function is considered as a continuous random variable. The probability distribution of a continuous random variable is called as probability density function. Now, probability mass function is generally expressed in the form of a table. That means we give the values of x and we give the different probabilities for different values of x represented in a tabular form. Since continuous probabilities or continuous random variable takes any value within a particular range, so it is generally expressed in the form of a function. The probability density function, on the other hand, is expressed through the help of a function, and that is called as the probability density function. Now let us go into the details of a probability mass function. Its x is a discrete random variable taking the values x1, x2, xn with corresponding probabilities p1, p2, pn. Then the probability function pmf is given by f of xi equal to probability of x equal to xi equal to pi, where I goes from 1 to n. Now let us see how we express this generally in the form of a tabular form. For example, x. Let us take the example of throwing of a coin 3 times. So it takes the value 0, it takes the value 1, it takes the value 2, it takes the value 3. Now if you remember, out of I give this as probability of x equal to small x. Okay. Small x, these are the values of small x. That means the values taken by the random variable. And if you remember, in that case, we have only one case out of 8 cases where there were 0 heads, and only one case out of 8 cases that had 3 heads. Okay. So this is the corresponding probability of x taking the value 0. This is the corresponding probability of x taking the value 3. And we had 3 cases where x took the value 1. And there were 3 cases where x takes the value 2. So these are the values: 1 by 8, 3 by 8, 3 by 8, and 1 by 8. So this is the probability of probability values. These are also either written as this is written as either pi, or in a particular case you may also write them as f of xi. That is the required probabilities. Now, when you take the sum of these probabilities, that is summation of f of xi, summation of f of xi, this is equal to 1 by 8 plus 3 by 8 plus 3 by 8 plus 1 by 8. And you will find that this probability comes out to be 1. That means this condition is satisfied, that the sum of the probabilities should be equal to 1. This is not capital I, this is small I. And so f of xi for all I satisfied shall be positive, shall be f of xi for all I shall be greater than equal to 0. Certain probabilities might be 0 also, but all the probabilities should be equal. So this is one condition of probability mass function, that individual probabilities shall be greater than equal to 0, and sum of the probabilities should be equal to 1. So these are two important conditions for a probability mass function. Similarly, if your probability, similarly, if your random variable is discrete but has countably infinite number of values, in that case, we have x equal to, say, it takes the value x1, x2 dot 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 up to infinity, and with probabilities as p1, p2 dot dot up to infinity. So this way we write the probability function, and then this condition summation f of xi for all I shall be greater than equal to 0. This condition remains the same. Here only your I, instead of, in this case it was 1 to n. In the case of infinitely many, that is countably infinite number of values, it will go from 1 to up to infinity. So this way we actually define the values of the probability or define the probability mass function. Now let us look at the probability density function. The probability function of a continuous random variable is called as a probability density function. In short, we call it PDF and is generally written in small letters. Now, we know that a random variable x is said to be a continuous random variable if it can take any value within an interval a to b. So this is x is a continuous random variable. It takes any value within the range of a and b. Then the corresponding probability function is called as the probability density function. Probability density function has to satisfy some properties. They are, number one, that the probability function should be greater than equal to 0. That means these should not be less than 0. This cannot be negative. So probability at a point is generally we actually take the ordinate of that value. That means this height. So probability, this is probability of x. Now this is the range. That means in the entire range of a to b, the integration of the probability density function is equal to 1. That means it is nothing but the area under the curve fx. So this is the curve fx, this is the curve fx. So your integration from a to b, say this is the point, say this is the point a, and this is the point, say b. This point is called as b. Now integration of the entire probability function a to b fx dx, this is nothing but the entire area under this curve. So this is the entire curve. So this is the entire curve. So actually, when I take the integration a to b fx dx, we actually consider the entire area under this curve. That means this area, this entire area. So this area should be equal to 1. That is, in total integration of the density function over the entire range on which it is defined should be equal to 1. And then the random variable capital X. Okay, let me make this clear. Okay. And the random variable of that x takes values between two values, say x1 and x2. This is obtained by integration of that particular density function within the interval x1, x2. So you can see that this is x equal to x1 and this point is x equal to x2, and the probability is the area under this curve. So if you look at this entire area, so that area is measured, and that area is the probability that x lies between x1 and x2. For these, we cannot have probability at a point, because in case of continuous random variable, it is area under the curve. If you tell me that what is the probability that f takes the value x1, that is f of x1. So that means this line. So this is actually answer is equal to 0, because we measure the area under the curve. Now a line does not have any area. Upper limit is this, okay, lower limit is this part, but it does not have any area. So this probability at a point, this is very important. Probability at a point in case of a continuous random variable is equal to 0. Probability at a point for a continuous random variable is equal to 0, because we actually measure probability, we mean the area under the curve. Because probability, say f of x1 is only a line. This is f of x1. This is f of x1, this line. And this line is f of x2. F of x2. We can find out the probability from this point to this point, as you can see here, this area. But we cannot find the probability at a point, because probability of at a point gives you a straight line which does not cover an area as per the definition of a straight line. A straight line cannot cover an area. It has a length, but it does not have any breadth. So Following that, the probability density function does not have any area. Probability density function at a point that does not have any area, and hence the probability of a probability measured through a probability density function at a point is equal to 0. This may not happen in case of discrete random variable. Probability at a point is possible. Definitely, we have probability at some points. In some points, we will not have any probability, which where random variable does not produce any value. But at some point the probability will be accumulated. So this is the basic difference between a probability mass function and a probability density function. In short, probability mass function relates to a discrete random variable, relates to probabilities of a discrete random variable, and probability density function relates to probability of a continuous random variable. We go a step forward and now we introduce the mathematical expectation. In a very simple word, mathematical expectation is the average of the random variable, average value of the random variable. So let us define it, that if x is a discrete random variable, first we see the discrete case, then we'll go into the continuous case. So if x is a discrete random variable, so this is x is a discrete random variable, assuming finite values x1, x2 dot 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 up to xn with corresponding probabilities p1, p2 dot 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 pn respectively, then the expectation of x is given by summation pi into xi. That is, this is the sum of the product, which is called as sum product. Sum product of the values of x with its corresponding probability. Sum product of the values of x with corresponding probabilities. That means first we take the product of individual xi's with the corresponding probabilities, and then we take the sum of them. So this is represented by this summation of pi and xi. Now, first thing is that this series should be a convergent series if you want to calculate the expectation. If it is not divergent, then you won't get any expected value. First thing. Second thing, that sum of total probability is equal to 1. This we have seen earlier also, that this is a property of the discrete random variable. So this also holds in this case. And in similar manner, a discrete random variable with infinite values can be defined. So if it takes infinite values, then only summation formula is same pi xi. Earlier case, in this case, we had I equal to 1 to up to n, I equal to 1 to n. Here, I contain infinite number of values, so I starts with 1, can go up to infinity. So this is how the mathematical expectation for a infinitely countable series is concerned can be defined. Other properties like this should be convergent and total probability is equal to 1 remains to be the same. Now let us look at the mathematical expectation of a continuous random variable. So if x be a continuous random variable with probability density function given by f of x defined in an interval AB. So this is important. What is the interval in which your x is defined? Then the mathematical expectation of the random variable x is given by expectation of x equal to integration of a to b x into fx dx. That means provided that integration of ab fx dx equal to 1. That means, as we have seen earlier, that the total probability in the entire range of the density function should be equal to 1, and this is the integration. Now, this expectation of x is nothing but an average of the random variable, whether it is discrete or whether it is continuous. And this average expectation of x is the average of the random variable. Now, here we have a special note that in case you are asked to compute gx, that means a function of x, that means expectation of x is well defined. But if I want to compute expectation of x square, then what I will do? Now, this is actually, here we have gx, the function of x equal to x square. In that case, the formula is given by this. In case of discrete random variable, a to b gx fx dx. So fx is the density function, gx is the random variable or a function of the random variable. So we have, and discrete case, we have this I goes from either 1 to n or I goes from 1 to infinity. That is, probability will remain the same, but the value of the random variable may change from xi to gxi. In particular case, if gx equal to x or gxi equal to xi, then we go back to the definition of the mathematical expectation of x only. So in that case, that is, so you can consider that gx of x dx, that is expectation of gx, is a special case of expectation of x. Sorry, expectation of x is a special case of expectation of gx, because when gx equal to x, we end up the computing the expectation of the random variable x. So this definition of expectation of gx is a generalized one, whereas that of expectation of x is a particular case when gx becomes equal to x. Now let us look at some theorems of mathematical expectation which will actually help us to compute the expected value of different random variables. If c is a constant, then expectation of c is equal to c. For any constant, the expected value remains to be the same. If c is a constant and x is a random variable, then expectation of cx is c times expectation of x. That means if you know the expectation of x, just multiply it by c, then you get the c times of expectation of x. And expectation of ax plus c, that means from these two, we can derive this expression. This is derived from the previous two theorems. Expectation of ax plus c equal to a expectation of x plus c. Because how we go with this? We go with this in this way, that ax plus c. Now expectation can move inside the summation. So I'll get expectation of ax plus expectation of c. Expectation of c. The expectation of x is a. Expectation of x plus expectation of c is c. So this is a expectation of x plus c. So this is how this proof is very simple, and it can be derived from the application of the previous two formula. Now there, let us look at if in case we have some random variables, what we shall do. That if x and y are two random variables, then expectation of x plus y equal to expectation of x plus expectation of y. And this formula holds both for the discrete case as well as for continuous case. So we are not segregating it as for discrete case separately and continuous case separately. If we want to look at the proof of that, then obviously whether it is discrete or whether it is continuous, that will only differentiate or create difference in the way things are deduced. In one case we will use summation, in the continuous case we will use integration. But overall, this theorem holds that expectation of x plus y equal to expectation of x plus expectation of y. And this can be extended also for more variables. That is, if we have three variables, say we have, let me make this little bit clear. If we have say three variables or more than three variables, then we have like expectation of x plus expectation of y plus expectation of z. These can be equated to expectation of x plus y plus z. That is, in other words, if we have expectation of x plus y plus z, so this is equal to expectation of x plus expectation of y plus expectation of z. So this is how we have the expectation. In particular, if we have expectation of xy, so this is equal to expectation of x into expectation of y. But this does not hold always. This holds only if x and y are independent random variables. Independent random variables. If they are independent, then and only then we have expectation of xy equal to expectation of x into expectation of y. So this is called as the sum rule, addition rule of expectation. This is the multiplicative rule of expectation. This is true for any type of variable, whether x and y are related to each other or not related to each other. This will hold, but this holds only if x and y are independent of each other. This can also be extended, like if we have expectation of x, y, and z, x, y, and z, and if in this case x is independent of y, y is means they are mutually independent of each other, then and only then we can have this only if x, y, and z are independent of each other. Now let us look at the variance of a random variable. Let x be a random variable where it might be discrete or it might be continuous. So x is a random variable which might be discrete or continuous. Then the variance of the random variable x is defined by variance of x equal to expectation of x minus expectation of x whole square. So this is how we define the variance. Now, this variation of a random variable is quite important, because once you have a random variable, you need to understand the mean so that you can understand where the average lies. And then variance will give you an idea about how the random variable is spread across the mean. Where if higher variance means it is more spread around the mean, lower variance means the spread is less around the average. So this is the formula for that. If you break this up, a minus b whole square formula, and then apply expectation, after a few steps you will end up here. That means expectation of x square minus expectation of x whole square. So this is generally used for computation because this gives us a simplified way of computing the variance. Then you use this formula. This is little difficult. This is easier to handle when you go for computational purpose. So we generally prefer the second formula for computation. However, when we define the variance, we define it with this formula only. Now, it has also some interesting properties, proof of which are available. We are not covering the proof in this part of the presentation. You can pick up any textbook of statistics and you can find out the proof of this, that variance of a constant is equal to 0. It is obvious also that it is measuring the spread. If the value is constant, it does not have any spread. It is always taking the same variable, same value for a given variable. So if it is a constant, then this variance is 0. If it is a Cx, that means a constant multiplied by a random variable, then C when comes outside becomes C square and we have variance of x. And then we have, based on these two, we get the extended formula of these. Variance of Ax plus C is actually variance of Ax. This can be written as like variance of Ax plus variance of C. Now C is a constant, so that is becoming 0. A coming outside makes you A square variance of x using this formula. So these are the three formula which we will require in computational purpose. So thank you for watching this video. In this video we had covered, we had defined a random variable. We have defined the different types of random variable like discrete and continuous. We have seen their probability function, which is called as the probability mass function for a discrete random variable, probability density function for a continuous random variable, and we have later introduced expectation. We have gone through statements only, obviously, the different theorems concerning expectation. Later stage we introduce the variance, and we have also looked into different theorems that are concerning the variances. So in the next video, which is part 2 of this presentation, we will actually do all computations related to the theorems and the definitions that we have learned in this presentation. So just keep waiting for our next video. Thank you for watching this.